Well, thank you for attending. In fact, when I was invited, I wasn't sure anymore, but I checked, and I already gave a keynote address at EASE in 1999. So that does not make me feel younger, but that's actually a fact. Today, of course, I'm going to talk about artificial intelligence in software engineering, and not software engineering for artificial intelligence systems. I would like to, of course, thank the organizers for inviting me. And I will be pleased, of course, to take questions after the talk, and stay as long as you want to discuss whatever topic you may be interested in. First, let me define what I mean by artificial intelligence. As you know, this is an overloaded phrase. So I don't only mean machine learning. I actually mean also natural language processing, any form of logic-based reasoning, and different search techniques, whether they are metaheuristics like evolutionary computing, or exhaustive like SMT solving, or constraint programming. I would like to maybe start with an anecdote. When I was a PhD student in 1991, I was in the US doing my PhD at the University of Maryland, and working for the Goddard Space Flight Center. And at that time, they wanted to be able to predict faults in flight dynamic software, to understand where faults were located, for which reasons, and try to use that to drive their validation and verification, code reviews and stuff like that. And just to tell you how things have changed, at that time, I was very strongly scolded by my colleagues and student friends for using machine learning, because that was considered a maverick field that was not to be taken seriously and that had no future. So it's kind of funny to see how things have evolved. The objective of this talk is to report on many years of experience about leveraging AI on industrial research projects. It's not a survey. I am going to report on a personal experience, and therefore, of course, it's going to be a very partial presentation. I picked some examples, recent examples, most of them, and based on that, I will try to draw lessons learned concerning real problems, real solutions, and real industrial contexts. So, at the very beginning, in the 1990s, people were very worried about making software development more predictable in terms of predicting resources, predicting defects in various forms. That was the main focus. And the context was that there were very few software development data repositories at the time. So data was scarce and hard to use. And actually, I was very lucky to work in the Goddard Space Flight Center, because that was at that time one of the few places in the world where software development data was actually collected. Research was very much focused on predicting any form of resources, effort, defects, as I said earlier. Hundreds of research papers were published, and hundreds more were published since then. You just have to look at proceedings of major conferences or journals. And I was actually part of that trend at the time. One of the last projects I worked on regarding this topic was actually in Norway, since EASE is taking place in Norway this year. And where we had, in 2007, a project, Telenor, a major telecom company in Scandinavia and Northern Europe, where they wanted exactly to do that. That is to somehow use information regarding a change request concerning classes in a telecom system, the characteristics, structural characteristics of those classes, and also their change and fault history in order to predict whether a class for a given build, a given release, was going to be faulty or not. That work was actually published with some of my colleagues in Norway, and was the last piece of work I did related to that topic. And of course, we use machine learning for obvious reasons, is that the data we were using were very complex. We couldn't really make assumptions about relationships. So machine learning was a natural way to address that problem. So we also built visualization mechanisms. Here is an example of a tree map for people to be able to look at where faults were expected, which part of the system, faulty classes and faulty components being in red here on the picture, and we gave them some form of interactive system to be able to use those prediction and that type of data. And what is the point usually of those prediction models is that somehow you collect data from change, faults, and human activities. You learn about fault patterns. You use those fault patterns to somehow focus VNV, focus code reviews, focus unit testing, or whatever that is. And the idea is that somehow, hypothetically, this helps you better make use of your limited resources, for example, your VNV resources. However, what we found out in practice is that mapping those prediction models somehow to optimal VNV practices was not that easy. It's not that easy to come up with a strategy that makes effective use of such prediction models. So that was an example. And to summarize, machine learning for prediction, as we know, they are now pretty computationally intensive, but very effective techniques, in particular ensemble techniques, such as random forest, that tend to be more flexible and robust and less prone to overfitting, which is what we need for the type of models we are building. And as larger amounts of data became readily available, the application of such techniques became more and more effective. That was the case in particular with the rise of mining software repositories. And beyond the predicting resources and defects, many more applications, many more prediction models have been built. For example, in testing, people have been using machine learning for test selection and prioritization to predict flaky tests or test dependencies. And based on available work, it's not perfect, but it works reasonably well. However, there are challenges. I've never seen a company building and maintaining a corporate prediction system over years in a sustained way. In a given organization, we are predicting moving targets, our development practices change, people change, systems evolve quickly, and it's not easy to deal with such evolution in practice and somehow update your prediction systems. You will notice, as I briefly mentioned, that there are a lot of papers on how to build prediction models of all kinds, but there are very few papers on how to effectively use such prediction models and assess their benefits in practice. So you always, hear urban legends about people doing things, but there is very little that is being reported regarding this. And in practice, it's not that easy, actually, and maybe that's the reason. All right. After that, in the decade after that, when the next decade started, another form of artificial intelligence technique started to rise and in the software engineering literature. And that's what people refer to as search-based software engineering. Why search-based software engineering? That short paper by Harman and Jones was the first one. I think it came out in IST, Information and Software Technology, if I'm not mistaken. And it was the first paper actually to coined that phrase, search-based software engineering, because the main motivation is that after decades of research, there were a lot of automation problems in software engineering that were not resolved, for which there were no scalable practical solutions. And formal methods and theorem provers and model checkers, were not up to the task. Whether you talked about automated test data generation or many other problems that I will mention. And people started to realize that many automation problems, such as test data generation or test case prioritization, could be re-expressed as a search problem. And people then started to use meta-heuristic search for reasons I will briefly mention later, which are form of stochastic optimization algorithms. So basically, in other words, many of those automation problems could be re-expressed as automation problems. And then little by little, people started to realize that those techniques had a very wide potential and that their application somehow formed a research topic in itself. So you know what optimization is. Somehow we are trying to find in complex landscapes global optima. And the reason why people use meta-heuristic search to do optimization is when there is no closed form analytical description that somehow links the inputs of the search space to the fitness function. And therefore, all that means that somehow optimization is black box. And that's when those techniques typically in many fields of science are used. And in software engineering, we are very often in that situation. For example, there is no closed form analytical description linking the inputs of the system with their outputs and therefore the fitness functions resulting from those outputs. All right. So examples of such meta-heuristic search. The most well-known one are genetic algorithms that somehow emulate the natural evolution process. So it's inspired by evolution theory. I won't go into details. And another personal anecdote is the first time I basically read about genetic algorithms was in roughly 1995. The well-known and now somewhat outdated book from David Goldberg. And my first reaction is that this must be a joke. I mean, this cannot be serious, I was an engineer by training and, I'd been trained in mathematical optimization techniques. And when I read this, I thought, this must not be serious, And it was actually a very good personal lesson for me to always keep an open mind. Because given the number of times I've used meta-heuristic search techniques in the 25 years after that, I should probably have kept my mouth shut. Let's put it that way. So let's take an example from one of our recent projects that we used to draw some lessons learned. So there are many applications where people are doing so-called key points detection in images. So, for example, in an automotive context, it may be used for drowsiness detection. If you have a camera in the car and that is somehow filming the driver. And the key points here are the different features of the face, the corners of the eyes, the tip of the nose, stuff like that. So those key points are predicted in order also, for example, for face recognition and many other applications. And of course, it's essential to actually test the deep neural networks that are doing key point detection in order to determine whether they are accurate, the predictions are accurate. So our problem is that what we want is that, in fact, each key point is a requirement and therefore matches a test objective. And in that particular case, which is a project with a company, an automotive company called IE, they had 27 key points that they needed to predict, for example, for drowsiness detection. And also because they wanted to have redundant key points in case some of them were hidden because of the position of the head of the driver. What we did here is that actually we used a search algorithm inspired from genetic algorithm, except that it's a so-called many objective search algorithm for a reason I'm going to mention next, combined with a simulator in order to be able to detect the accuracy of key point detection and compute fitness during the search. So this was work done with my colleague Dongwan Shin and Fitash Ulhak, and to appear at ISTA soon. So to give you an overview of how it worked, we have an input generator which is based on that many objective search. The inputs is given to a simulator that generates a test image. The DNN takes the test image and input a deep neural network, predict key points. We get the actual key points from the simulator, compute the fitness, and pass that fitness value to the input generator. And why, and of course, the goal, why do we do this, is that eventually what we want to do is to generate worst case inputs or worst case images where the prediction of key points are pretty bad, like on that example image below. And why do we use a many objective search? Would you come up with, why did we use that peculiar search algorithm? Is because our 27 objectives, or 27 key points match somehow 27 fitness functions that are rather independent, and we are not doing Pareto front optimization. What we want are test cases that somehow, in the case of the diagram here, minimize at least one objective, regardless of the other objectives. And so those many objective search algorithms have actually been devised as a modification of genetic algorithms to fit testing problems, automation or test automation problems. So I'll come back to that, but basically algorithms have to be modified to fit our particular needs in test automation. So we got pretty good results. We found actually a lot of problems with a lot of key points in that industrial system, which was not really surprising. The main reasons were that many key points were underrepresented in the training data used to train the DNN for various reasons, because they were hidden, for example, due to the position of the head. And also certain things were hard to predict, like the mouth, because there was a large variation in shape and size of the mouth, and therefore more training was needed. More training data was needed with variations in shape and size of the mouth in the image. But it's important to realize, those results may seem surprising, but it's important to realize that not all these predictions are failures in such a context. The system, for example, to do drowsiness detection, doesn't need to use the 27 key points or predictions. And therefore, depending on the position of the head, only a subset can be used, the appropriate subset can be used, where there is no shadow and where the key points are clearly visible. And we use machine learning, in that case regression trees, in order to draw, in order to learn from the test results, rules that somehow characterize situations where key point detection is very accurate, or conversely, extremely inaccurate, which is case number B here. And those provide basically insights in terms of why, in some cases, key point predictions are inaccurate. And for example, due to the position of the head, the presence of the shadow, like on image B here, where it's not possible to predict the corner of the mouth, the left corner of the mouth. Which can be understood. Every deep neural network, of course, has limitations. And also, we could actually also determine that we were able to very accurately predict when the DNA will provide a good prediction or not. And this, of course, is very useful for various reasons. So, of course, this is an example. There are many applications of SBSE, from requirements prioritization to refactoring and code refactoring, test automation, of course, I give an example, program repair, a very, very varied and large number of applications. My first SBSE paper, another personal anecdote, was at CIKI, I think an different conference that used to be the main conference for software engineering and AI in 2002. So we did the research work at the same time, more or less, as the Harman and Jones paper. And it was in the Italian island of Ischia. And I remember it very well because I basically fell asleep on the beach after 21 hours of traveling from Canada. And I almost missed my own talk, but I woke up in time, fortunately. Yeah. And since then, of course, many of my articles have a search component as one element of the solution. And because as it turned out it to be an essential piece of solution for many of the problems I've faced in industry. So to generalize from my experience regarding SBSE, sorry, it's an effective automation mechanism for a wide set of software engineering problems. Potentially, it has a higher scalability, with scalability being always an issue in software engineering, because it's not based on exhaustive search. But it's effective only under certain conditions, which depend on the search landscape, the time taken by the fitness computation, how effective are your, for example, genetic operators, if you use a genetic algorithm, and all that. Another thing that is good about it is that many of those algorithms, like the genetic algorithm, can be effectively parallelized, which also helps with scalability, especially nowadays when we have access to so many multi-core computing resources. There are challenges. Performance can still be an issue. There is always a limit to everything. And in software engineering, we often face problems with high dimensionality search spaces. Or more often than not, the fitness functions are expensive to compute, especially, for example, if they involve a simulation in the loop, like it's often the case when you test, let's say, cyber physical systems, such as advanced driving automation systems. Validation is experimental because those are heuristics. And they are often computationally expensive. I mean, demonstrating experimentally that a given search-based approach works is extremely expensive and requires usually often days, if not weeks, of computation, even on a multi-core platform. Very often, as you have seen an example with the many objective search algorithm, trying to determine what is the best search strategy for a given problem is not obvious. So it requires some degree of expertise. So that means that using that approach in practice for practitioners without a tight collaboration with researchers is not obvious. And devising also the right fitness function is often a trade-off. Often you have the choice between a very precise fitness function that is very expensive to compute, or a more approximate fitness function that provides a more approximate guidance to the search, but which is faster to compute. And it's hard to know what is the right trade-off. Starting maybe in 2005 or roughly about that time, natural language processing techniques became increasingly powerful. And even in the last 5 years, they have evolved a great deal, as I will mention. And this was, again, an opportunity for software engineering. So you know what NLP is, probably. It's about all those techniques that I use to process and analyze large amounts of natural language data. It used to be in the early days rule-based, and it became statistical, basically nowadays based on machine learning and even deep learning. So you know what are all the techniques that are usually involved in NLP, pre-processing techniques, parsing techniques, and more recently, so-called language models that are based on deep learning that basically learn languages, which can be, requirements in a domain, source code in a given domain, and somehow those techniques, are the subject of very intense investigation nowadays, and you see more and more papers in software engineering review based on that, using BERT or variance, for example. So why NLP? For obvious reasons, I guess, is that in software development, most documentation is in natural language. It may be constrained, but it's natural language. So, for example, most natural requirements are in natural language. And this is very prominent throughout industry sectors, even safety critical ones. And it hasn't changed in 20 years. It's not like people are slowly giving up natural language requirements. They are not. That's still the most prominent practice in 2021, and it hasn't changed in 20 years. So what can NLP be used for? It can be used to check the well-formedness of NL artifacts, such as requirements, extract useful information from natural language artifacts. For example, we see an example where we use that to automate system testing, check consistency and completeness, for example, of requirements, understand relationship and dependencies between natural language artifacts, for example, to establish traceability between requirements and test cases, especially if you have test specifications. So in order to manage traceability automatically, traceability being a requirement by many standards in many safety critical domains. So in requirements engineering, with many colleagues over the last year, I've used NLP for many, many things in requirements engineering, check conformance of requirements with templates, impact analysis of requirement changes, identification and demarcation of requirements in large documents when requirements are mixed up, which is often the case, with other textual information. And we have done that in industrial context. It worked well, it was accurate, it was scalable. And this is something we could not have done 10 years ago, with the state of technology 10 years ago. And I'm going to walk you through an example of requirements-driven system testing relying on NLP. So that example is again the automotive domain. Of small but safety critical embedded systems where people have to establish, as I've mentioned before, in order to comply with industry standard, traceability from requirements to test cases. It's often required. Requirements also act as a contract. And also there are many requirements changes, like in most contexts, leading usually to negotiations between the company and their clients. So traceability in that domain is required not only by standards, but often by customers and certifiers, because they also want to make sure that somehow the requirements they agreed upon have been delivered, have been addressed. If requirements change, test cases have to change as well. And then given the size of the system, even small system, embedded systems, the traceability matrices that have to be maintained and manually built to demonstrate compliance are basically unmanageable in practice, based on what I've seen. Though that's the practice. So there is academic work for matching some automatically requirements to test cases. Until recently, it had questionable results. I mean, it was unclear based on the result whether that was really usable in practice. So the problem is then we were facing is how to then automatically verify compliance of the software system with the functional requirements in a cost-effective way, given that situation, which, as I said, is very common across many domains, in particular safety critical domains. So our objective with my colleagues, Chenny Wang, who used to be a PhD student of mine, now working at Google, and Fabrizio Pastore, who's a professor at the SNT, is how to support the generation of system test cases from requirements in natural language and have traceability of a byproduct. That's how we decided to tackle the problem. So, of course, you can already imagine what the problem is. Textual descriptions are often ambiguous, incomplete, and not analyzable automatically. So we thought, okay, we have to find a compromise somehow. So we decided to stick to natural language, but to restrict its usage so as to make it amenable to NLP for system testing purposes and find the right balance. And then we decided to rely on a piece of work done by actually Tao Yu during our PhD, a piece of work called restricted use case specification, and the reason why we did this was twofold. First, our partner was already writing use case specifications, not very well, not very consistently, not in a form that could be readily used for system test generation. But nevertheless, that was a practice. So we thought, okay, it's probably easier to help them write better use case specifications in that situation. And you know, there are many companies who write such use case specifications, and most of the time, not very well, not very consistently. But RUCM, supported by natural language processing, was a way for us to somehow, possibly, have them write requirements that would then be amenable to automation, system test automation. Okay. So, what RUCM specifications look like, we modified them a little bit since the original paper, but not that much. Is that the basic flow events in a use case is written according to a fixed number of categories for statements, where the various statements either capture inputs, output statements, include statements, or check conditions in order to run an alternative use case flow from the basic flow. And that methodology is based on both keywords that you can see in blue here and somehow grammatical rules that restrict the shape of the sentences. So we are able to know, thanks to this keyword, whether it's an input step, an include step, a conditional step, an internal step, and all that. And of course, conditional steps may lead to alternative flows. Once we know what those steps are, it's easier for us to identify so-called domain entities, such as in that case here, because we are talking about a seat occupancy system here, an embedded system that monitors the seat occupancy in a car and, for example, trigger airbags, for example, or not, or turn on airbags or not. This is useful because those domain entities usually correspond to either inputs or outputs for testing. Also, we're able to identify constraints or conditions. And those, again, as you can imagine, are also useful for testing purposes. So from such a use case model, we are able to derive a test model. Test model that basically represents all the different paths of scenarios, all the different scenarios that can be executed during system testing. And along the path, we have inputs, outputs, and conditions, among others. So we developed a tool called UMTG that took those use case specifications, but also needed to be complemented with a small domain model, a class diagram with all the domain concepts, something which is not hard to do and that we did with our industry partners, and the constraints along the execution path in order to generate system test cases. But as you can see here, the constraints are not in natural language. They are in OCL, the object constraint language, which is a standard language in model-driven engineering for expressing constraints. And I'll get back to that in a minute. So assuming you have those constraints in OCL, with each scenario, you can derive a path condition. That path condition usually, because those express system level constraints are quite complex, and therefore standard solvers or constraint solvers do not work for such constraints. So we had to devise a constraint solver called Pledge that actually smartly combined Metaheuristic Search and SMT solving in order to solve complex system level constraints. And then if you can solve such constraints, you can actually generate test data for all scenarios in your use case specification model. But again, we rely on the existence of constraints here in OCL. So of course, typically engineers do not want to write so many constraints. It's okay to write some, to modify some, but they are not particularly happy about writing dozens of OCL constraints. So what we did is that we resorted to natural language processing in order, with a tool called OCLgen, to go from natural language constraints like this to constraints formalized in OCL. And the way we did it is by relying on natural language processing, a quite advanced technique called semantic role labeling that helps identify automatically in a sentence the roles played by words or phrases according to some categories, such as the actor affected by the verb or the final state. There are a number of categories. And then somehow we match those phrases or words to concepts in our domain model, in our class diagram. And then we have basically verb-specific transformation rules, not that many. Maybe there are 7 categories of verbs based on VerbNet, which we can use, for which we define transformation rules to go based on the identification of phrases or the roles of phrases and words in a sentence in our RUCM to OCL based on a domain model, a class diagram. So, and it was actually, I don't have time to present the details, but it actually turned out to be very accurate, by the way. We were able to generate mostly correct and complete OCL expressions that then could be refined by engineers. So, to summarize, NLP in software engineering, increasingly powerful, many applications, wide variation across domain practices and documents. So that means you always have to somehow adapt whatever is your NLP strategy to, the way your documents are written in a given context. Of course, there is, you don't fully escape the inherent ambiguity and inconsistency of natural language. And often that information is spread even across several documents. So that means somehow you always have to try to design and experiment the right NLP pipeline in your context. And it's not easy. Of course, no matter what you do, NLP components are never fully accurate somehow. So you have to see how you can deal with that degree of inaccuracy, for a given application. More and more people, as I said, people rely on language models such as BERT and all its variants, code BERT, whatever, Roberto, there are many. But even though people are working on this, they are computationally extremely expensive, which in some contexts is not always an option. So what does that all mean is that somehow the human is in the loop. And the question is always, what is the role of the human in all this? Sometimes it's pretty obvious, like in my example, where engineers are supposed to check and refine and complete OCL expressions, but it's not always that obvious. All right. So I went through using machine learning for prediction, using search techniques for automation through optimization, and natural language processing to somehow deal and exploit information in natural language form. However, in practice, those techniques are used together most of the time to solve a problem. And I'll try to give an example and somehow draw conclusions. In practice, and actually you have seen that in some of my examples, in practice, single technology rarely works by itself. So it's not enough to use Metaheuristic Search or even machine learning alone or NLP alone. And so very often those have to be combined with solvers, such as SMT solvers, and I'll show an example next, or even statistical approaches like sensitive analysis, dimensionality reduction, things that come to mind, and even, of course, system and environment modeling and simulation. And we have seen an example for the key point detection problem, where we had a simulator in the loop. So if I take another example with my colleagues, Kul Galul, Klojo Mengi, and Shivani Jati, in collaboration with OHB Logspace, a satellite company in QRA, verification tool company in Canada. We had a project about mining assumptions satisfying requirements. I will explain that now. So in a cyber-physical system, people design usually or develop models in languages, in simulatable languages like Simulink or functional languages to model the environment of the system, the hardware, and the control and decision algorithms of those autonomous cyber-physical systems. And those models, of course, have to be tested. You have to check that they somehow fulfill requirements, like any piece of software. This is no different than regular software. But often those requirements are only satisfied under certain assumptions. And what we noticed is that in this environment, like in most environments, people rarely document assumptions. They don't have a document that says, oh, that requirement is only satisfied under that condition. So the question is that how could we somehow retrieve those assumptions to help people identify them and make sure that when testing a Simulink model, they would test the model with valid test inputs, for example. So an example is an altitude control component. You can imagine it's a Simulink model. And there is a requirement that says that when the autopilot is enabled, the aircraft altitude should reach the desired altitude that is specified within 500 seconds in calm air. However, that model did not always satisfy that requirement. Sometimes the plane did not reach the desired altitude. And the reason, of course, is pretty obvious. It's very intuitive. That's why I use that example. The reason is that there is an assumption. And the assumption that has to be somehow inferred is that the pilot is in charge to provide, to adjust the power of the engines for the aircraft to be able to reach the desired altitude and not reach a stall condition. So what we did is that we developed, and this is part, by the way, of the PhD thesis of Kul Galul, we developed a technique that combined three different technologies that I've mentioned. A tool called Estalero, which is basically based on smart sampling, it's a form of search, to generate test scenarios that lead to failures or that pass. Then we use, we try two different things. Both simple machine learning, such as decision trees, or more complicated search, the techniques such as genetic programming, in order to learn from such data, to learn assumptions from the data generated by Estalero. And then once we identify candidate assumptions, we need to make sure that the requirement was indeed always satisfied under that assumption. And for that, we use model checking based on Z3 and SNT solver. So you see how we combine those different components in order to obtain a complete solution to learn and verify assumptions satisfying requirements in Simulink models. Conclusions. Metaheuristic search, indeed, for most automation problems can be expressed into an optimization problem or a search problem. They are versatile. That is, I've really seen an automation problem that could not be addressed by search, not more or less effectively, more or less efficiently, but most of the time, most often than not, the result was pretty good. Parallelizable, as I said before, it's very, very useful nowadays when basically multi-core computing has become a commodity. But it's not always easy to use and deploy for practitioners for reasons I've mentioned before. There are still scalability issues. Still, the choice of the search algorithm is not always obvious, and massive experiments are required for validation. However, we have seen an example, but I could have shown you more example. It can often also be effectively combined with solvers, and that tends to help, partly help, with some of those problems. Machine learning, very useful, as probably most of you already know, when you need to build somehow a prediction model based on complex data and that model complex relationships, for which you have in particular, very little theory, and you cannot really make assumptions. It also, and we haven't seen much of that, unfortunately. I didn't have time to show an example, but it's also very useful to combine machine learning with search in order to guide the search towards interesting parts of the search space, to try to predict automatically what are the parts of the search space that are likely to produce optimal fitness values, and therefore help guide more effectively the search. I didn't have a chance to show you an example of that, but if you have questions, I can go into more details. It complements NLP, because very often when you analyze natural language in order to retrieve information and classify, for example, classify requirements into functional or non-functional, or classify requirements into different categories, security requirements or whatever, automatically. Usually, if you look at the papers coming up with deterministic rules, it's not easy. So you need to somehow extract metadata associated with requirements and somehow predict or classify based on that metadata using machine learning. Accurate deterministic rules are not often an option. And more importantly, in this, we have seen an example with the key point prediction example I've presented before, when we were testing that deep neural network, predicting key points on a face. It helps understand actionable patterns. It helps, for example, interpret test results and understand what are failure conditions. Remember, we were able to actually, using regression trees, identify very accurately when a key point prediction was accurate or inaccurate, and why. It was then easy to actually interpret why by looking at the rules from the regression tree. NLP, we have seen an example with the requirements-driven system testing, helps exploit information in natural language, and therefore pushes the boundary of automation further, given the prominence of natural language in many software development artifacts. For example, requirements. Extract useful features for machine learning. For example, You may use natural language processing to extract information from test cases, test case specifications, or the source code of test cases, and somehow help predict whether they are flaky. People have done that. Or whether there is a dependency between test cases because they test similar functionalities, stuff like that. And also with language models, more textual transformations. There are newer learning paradigms I haven't mentioned. Obviously, deep learning, active learning, reinforcement learning. Those are potentially very interesting in software engineering. Actually, I have a few papers where I've used, for example, reinforcement learning to automate test case prioritization in continuous integration environments because it has interesting properties. For example, reinforcement learning has an interesting property of enabling continuous learning as new data is collected and not having to rebuild models from scratch on a regular basis. So basically, models are updated in a seamless way as data is collected. And this is very important in a continuous integration environment where you have a very little time usually to determine test case prioritization. You have a very quick cycles or build cycles. We have used also active learning, for example. Many people have used deep learning for many things, like predicting traces between requirements and system test cases in the last ICSI. But we still need to understand better in which software engineering context or which problems they are truly our best option. We don't want to use those techniques because they are fashionable or they are hype. Very often you have papers using those techniques and you are not sure why something simpler was not employed. So for many software engineering problems, actually classical machine learning works well. And very often the most important part, as you have probably experienced, is to find or to come up with the right features that can be used in input by the machine learning algorithm. And this is where usually the main difficulty is and where a lot of the thinking and experimentation goes. You may also have heard, I'm not going to talk about that, but I thought I would briefly mention it because you have increasingly many papers on the topic. So it's not AI for software engineering, it's software engineering for AI. Obviously, as more and more people are using machine learning components, such as deep learning components, into the systems, it has actually an impact on software, on the way software systems are developed. There is a paper from ACIP 2019, for example. It's quite interesting. There's a lot of people from Microsoft, if I remember correctly. And for example, a very active area of research in which I also work is on how to test and debug deep neural networks or systems that rely on deep neural networks, how to ensure their safety, given that all those machine learning components have no source code and no specifications. Their behavior is learned from data. So what is the road ahead? AI clearly plays a key role in automating many software engineering tasks and support decisions. As we have seen, real solutions really involve several techniques combined to achieve the best trade-off in a given context for a given problem. Usually, real solutions need to strike a balance in terms of scalability, practicality, applicability, and getting optimal results. And striking that balance is not always trivial. So what that means that research in this field cannot be oblivious to context, to the domain, because striking a balance can only be done based on working assumptions and knowing clearly what are desirable trade-offs. So to conclude, we need more multidisciplinary research that are driven by well-defined problems in actual well-defined context with clear working assumptions, for example. So that leads me to my usual rant on the academic industry gap. Many academic papers, though well written and clever, address problems that are unlikely to exist as defined, based, for example, on the stated or unstated working assumptions. On the other hand, there are many industrial problems, often that are long-standing, that are insufficiently addressed by research. For example, that is the case of traceability research, for example, traceability between test cases and requirements, but traceability in general. There are very few researchers who work on that because it was a hard problem, it was hard to publish. But there has been a problem for at least 40 years in software development in critical systems. And of course, you cannot usually find an effective solution in a vacuum. You need to have a clear idea of the targeted context. For example, you want to work in autonomous cyber physical systems in the avionics domain, then you know clearly what are the trade-offs, what's acceptable, what is required by standards, what technologies are being used, Simulink or other things, and then you can actually come up with a solution that is workable. And also often scalability and practicality aspects are largely ignored. If, for example, an automation technique that you devise requires certain inputs from the user has to be in a position to easily provide those inputs. So if you require very complex property in temporal logic, some form of temporal logic, and you are in a context where people cannot deal with that, then your solution is not practical. If your temporal logic properties are more complex than your source code, then again, the trade-off is unclear between the automation solution you provide and the benefits and drawbacks. There is a very good, paper by Ben Schneiderman and a book, actually, there is a book as well, very interesting on how somehow to create that type of collaborative research, what are the benefits, what are the ways to do it in engineering disciplines in general. Ben Schneiderman is from, user interface research or user interaction research. He's not from software engineering, but whatever he writes in his papers and his books is very relevant to us. And also a paper that I've written with my former PhD advisor, Vic Basile, and other colleagues on, how to perform that type of collaborative research that you can find in IEEE software. And I'm done. And if there are questions, I would be very pleased to, questions or comments, I would be very happy to discuss.